So today's lesson is built on the previous lesson on thermochemistry heat exchange. Today we're looking at the heating curve for water. It's just taking that whole concept further down the road. And today we're going to be looking at a second equation that's used when water is not being heated, but when it's changing phase. So what we're going to produce is something called a heating curve for water. Okay, now we're assuming here this is taking place under atmospheric pressure and not under some kind of extreme pressure or very low pressure. And we did say yesterday that heat capacity value assumes constant pressure, okay, for what we talked about yesterday. And so if everything's at atmospheric pressure in the same room, roughly at the same time, you're going to have constant pressure.
What does that say?
Under atmospheric pressure. What I want to look at here, and what I want you to look at, is what happens is, as we add heat to a sample of water, what happens to the temperature? Remember, we said temperature and heat are two different things. Heat is an energy, okay? And energy is defined sometimes as the ability to do work. Temperature, on the other hand, is a relative measurement of the amount of stored energy in a substance, okay? So what I want to look at is what's happening to the temperature as I continue to add heat energy to a substance, okay? Thought you had a question. No, okay, all right. Now, what is the freezing temperature of water? Very good. I'm glad you didn't use that F word. 0 degrees Celsius. Let's say we're going to put that right about here. Okay? 0 degrees C. Okay? And where you put it doesn't have to be exactly where I put it on the graph. Okay? And what's the boiling temperature of water? 100 degrees Celsius. Okay? I bet y'all don't even know what the Fahrenheit temperature of boiling water is, do you? Huh? Oh, very good. You do know. Good for you. But 0 and 100 is a lot easier, yes? Okay? 0 and 100 is a lot easier, yes?
Yes.
Okay. And you need to know those. Those are just values you need to memorize if you don't already know that. The freezing temperature of water and the melting temperature of water is 100 degrees C, and the boiling temperature, it's 0 degrees C and boiling temperature is 100 degrees C. Yes? All right? Now, we're going to be looking at what happens when we have ice, we have liquid water, and we have steam. But in between ice and liquid water, what's happening? You've got to melt it, yeah. So not only do we have liquid water we're going to put here in the middle, that's somewhere in the middle, doesn't matter exactly where it is, just somewhere in the middle, that's liquid water, and somewhere over here has got to be ice, and somewhere up here has to be steam. Okay? So this range here is for liquid water. Liquid water. And in this range, if we're adding heat in this direction, we're heating up the water. Would that make sense? So this is the heating and cooling range of liquid water. All right, down here we have ice, okay, which is solid water or frozen water. Yeah. Okay, and we're in this range here, we're also heating and cooling. We're adding energy to it to heat it up, or we're removing energy from it to cool it down. And this last section over here on the far right, what's that going to be? Steam, which is what kind of water? Gaseous water. And what are we going to be doing over there? Well, boiling is actually in this range. We'll talk about that in a minute. If it's already gas, we can heat and cool it, but we don't boil it if it's already gas. Okay? So up here we're going to have steam, which is gaseous water. And this is the heating and cooling range for steam we're talking about here. Okay? So ice, liquid water, and steam. And in between, you got to change from one to the other. All right, so in this range, then, we must be doing what to the water? Melting, or what if we're cooling it down? What are we doing with it? Freezing. Okay, so this is the melting and freezing range. Okay, and we call that a phase change. We're changing from a solid phase to a liquid phase. Okay, and what are we doing up here or over here? If we're going from liquid to gas, or from liquid water to steam, what are we doing there? Boiling, sure. And that's if we're changing it from liquid into gas. What do you call it if you're changing it from gas into liquid? Condensing. Mm-hmm. And that's also a phase change. All right, so this point right here, okay, that's the point at which we have stopped heating up ice, or the solid water, and we start to melt it. But what are we're adding what on this horizontal axis here? What's the variable down here? Not temperature. Temperature's over here. Yeah, this is the heat energy we're adding. Remember, temperature and heat are two different things. What we're looking at here is the effect of adding heat on the temperature. Okay? So we're going to be adding heat energy down here. And if we go in that direction, it's increasing the heat energy. Okay? And over here on the vertical axis, we're increasing temperature going in this direction. All right. Now, we looked at some calculations yesterday where we were adding heat energy to ice, and we saw that the temperature could increase. That was part of our problem we worked with yesterday. So as long as we're adding heat energy to ice, the temperature goes up. If we take heat energy away, the temperature is going to go down. The amount of energy in the universe is constant. Okay? So we're either moving energy from one place to the other, or staying steady where you are, and that's all you can do. You can't increase the amount of energy in the universe. Okay? It's constant all the time. All right? But you can increase the temperature if you add energy. Move the energy from place A to place B. Okay? If we're putting the energy into water, or into ice in this case, then we can increase the temperature. But while the ice is melting, there's no temperature change. You keep adding heat energy to it, but the temperature does not go up. It's supposed to be flat there. Okay? And we looked at the equation yesterday that fits in this range. What is the equation that defines how the amount of heat is related to the amount of temperature, or the temperature change? What's that equation? Okay. Heat capacity, okay. Change in temperature, okay. That's the equation that shows how Q, adding heat energy as Q, is related to the temperature change, which is on this axis over here. So the horizontal axis is Q, the vertical axis is T. Okay?
Why did he draw a box?
What box?
That one, the dotted line.
Oh, just showing that this is at 0 degrees C, and this is the point at which we go from ice, solid ice, to the melting range.
Yeah, you step straight up with the other line.
Well, I just went up there to show that this fits in this range right here. I wanted to make sure we didn't get confused that it goes somewhere else. It only fits right in this area, where we're increasing the temperature as we add the heat. Okay? Now, the specific heat of ice, or the heat capacity of ice, is, let's make that CP equals 2.0, where are we? 2.05 joules per degree C per gram. Okay? So this value plugs in right there. Okay? But right here, there's no temperature change. So why can't we use this equation here? There's no temperature change. We can't use it there. If there's no temperature change, it won't work. I mean, if you had a 0 right there, Q would be 0, right? No matter what I put in here, if temperature change is 0, Q is going to be 0. And there is obviously some heat being added, yes? So we need a different equation, okay? And so the equation we use here is Q, because we're still looking at the heat exchange, is equal to the mass times something called change in enthalpy. Now the reason it's H there is because most of the time we are talking about heat. In fact, one of the descriptions or phrases used to label what delta H is, or just explain what delta H is, it's the heat of fusion. Okay? But it really is something bigger than just heat. It's a lot of kinds of energy called, we call that enthalpy, E-N-T-H-A-L-P-Y. H stands for E-N-T-H-A-L-P-Y. Enthalpy. Okay? And enthalpy is, or can be thought of in high school chemistry as stored energy. What? E-N-T-H-A-L-P-Y. Enthalpy. It's the amount of stored energy in a substance. Okay? It's a little more complex than that, but for high school chemistry, that's a reasonable approximation of what it is. Okay? Now, there is a value for that delta H. And while we're melting ice, or while we're freezing ice, the enthalpy of that, or that process, is 334. So let's say that's delta H. The change in delta H is going to be 334 joules per gram. Since we're not changing temperature, there's no temperature term on the bottom as there is in heat capacity. Okay? Now then, once we're at liquid water, we've added enough heat that we've melted everything. We're now at the liquid water phase. So here's the boundary line where we're no longer be working with. We're no longer going to be working with melting the water or freezing the water. We're now into the water range. We can change the temperature again, the liquid water range. Okay, and we're going to go up to 100 degrees till we get right here. Okay. And we can increase the temperature as long as we're adding heat until we get to the point where it does what? Boils. Okay? Yes? Now, as long as we're changing the temperature, what equation can we use? The first one. Q equals mass times specific heat times the change in temperature. Yeah, we can do that. And does anybody remember what the specific heat is for liquid water? We used it yesterday. Nobody remembers? Hmm? All right, as long as we're boiling the water, or as long as we're condensing the water, the temperature stays constant. It doesn't go up. So since the temperature is not changing, what equation do we have to use? The enthalpy term. Mass times change in enthalpy. The enthalpy change value for changing liquid water into steam or condensing steam into liquid water is 2,260 joules per gram. Pretty big number. And the fact that that's a big number is one explanation for why steam burns so badly. It's not the steam that burns you. It's the condensing of the steam on your skin that burns you. Because it transfers that heat energy to your skin. Actually, the steam, where'd I get it from? Somebody's done the calculations and figured it out, or done the lab work to figure it out. And you can look it up in a large compendium if you wanted to, but it's pretty common. You can look it up anywhere on the internet. But there are, if I can find mine. There it is. There are these large reference books that have nothing but known values and things like that in chemistry. Okay? This just happens to be an old copy of the CRC Handbook of Chemistry and Physics. All right, I bet you know what happens next. That, yeah. She's doing her hand up like that, by the way, in case y'all didn't know. All right, you didn't say that? I thought you did. Oh, math. Okay, there's more math. Okay. Well, what kind of math do we put in here, in this range? What math fits in this range? Which equation do we use? If the temperature's changing, what equation are we going to use? The one that goes up? Yes. And the value of specific heat or heat capacity for steam is 2.02 joules per degree C per gram. Now next week, we are planning, I'm planning, I don't know what you're planning, I'm planning to have an ice cream lab.
We're playing the same thing.
You are? Oh, good.
Just as long as it ain't chocolate.
Just as long as you what?
It ain't chocolate.
It ain't chocolate? Well, you can decide. I'm only going to make the vanilla. If you want to mix stuff in there, you bring your own. You cannot share your condiments like chocolate or sprinkles or whatever, but you can bring your own. Okay? Now, here's the deal. These equations are going to be needed to do the math that you have to do to qualify to eat ice cream. Okay, so don't lose this. You're going to need this. Yeah, you got to qualify. Yes, right. And I'm going to give you some time to work on it. We'll lay it out for you. Huh? No. No. There's going to be a lot of ice cream. I don't plan to have a lot. I'm going to have enough for everybody to have a bowl.
I'm talking about go big, go home.
We're some big kids.
Go big, go home. Well, we're not going to do that. Let's see. Did I give you a copy of your test references yesterday? Okay, listen up, guys. These equations are found right here on your test references. Okay, there's some over here. I'll get it for you in a second. Or you can go get it. All right? If you weren't here to get your test, it's in your file. All right. Any questions about this?
So what we got to know for the ice cream? This?
Well, you're going to use these equations to do the calculations you have to do to qualify to eat ice cream. Okay?
We had some memorize those.
No, I just said that. Just got through saying that.
Come on.
They're right. The equations are on your test references. I've given you the equations. No, you don't need it. You don't need to memorize it. Just know how to find it.
So we need to know.
Okay? You good? That goes in your notes. So this goes in your notes, guys. General notes. Well, Unit 10. Yeah, it goes in Unit 10. Well, let's see. We can either do a practice problem or we can go over homework problems. What are you going to do first? Homework? Get out your homework, please. We have two homework problems. So this homework problem is asking you about the heat energy that's absorbed to raise the temperature from 25 degrees to 30 degrees C. Well, what range on this graph do you have 25 degrees to 30 degrees C? Where does that fit? Between 0 and 100. So it goes right here where we're heating up the water. We're using this equation right here. Does that make sense? You guess so? Well, you should know. Interpreting graphs like this is an important part of being successful in the science portion of the ACT test. Okay? So you need to be able to interpret graphs. All right? All right, let's look at the problem. The question is, does everybody have their homework out? Yeah. What I want you to do is exchange your homework with another student who's going to correct and grade your homework. Okay? Now, if you don't want anybody looking at your work, you can give it to me. I'll grade it. All right? I can't promise how fast I can get this back to you. All right, does everybody exchange their homework?
Oh, man.
Do you want me to copy that?
No, because I have to give you a makeup problem. I'll try to email it to you. If you'll email me, I'll send you a makeup problem, okay? All right, if you weren't here, then you need a makeup problem. You need to email me and ask for it, okay? If you didn't do your homework, you can make up a part of the points or grade, okay, but if you didn't do it on time, you don't get credit for it. However, if you do it, and it's done today, it's ready for me to grade it, or us to grade it, and you don't get 100%, you can do the makeup and make the whole 100% if you get it right, okay? If you do your homework on time, you can choose to do a makeup if you don't get a good grade. That makes sense? And don't lose any points if you do it, before the test. Don't wait till after the test. That won't grade it then. If you don't do your homework in time, you're going to lose points, okay? If you don't do your homework at all, you're going to get a 0. Everybody got that? All right, here we go. How many joules of energy must be absorbed? Well, joules of energy must be Q. Okay, Q. To raise the temperature of 20 grams of water, well, that means we're working with a mass of water. And then it's going to be times the specific heat, and times we're going to change the temperature from 25 to 30 degrees C. That's a change in temperature. Okay, there's our equation. All right. And to figure out change in temperature, it's always calculated as the final temperature minus the initial temperature.
Do we have to have the 2 things on top?
2 things on top?
Yeah.
What 2 things on top? These 2 things?
Those 2 equations.
You have to have both equations. Yes. Okay? All right. That's part of the points you get. All right, now, what I insist that you do for me is whenever you're adding or subtracting, you do it vertically so you can see what the significant digits are supposed to be. I know you can put this in the calculator, but if you put 30 degrees minus 25 degrees in the calculator, you won't get the significant digits. Okay? And if you don't add it up vertically, you won't see how to get the correct significant digits. So if the final temperature here is, we're going from 25 to 30, so the final temperature is 30. And so we're going to subtract 25. And so when we do this way, we can see that we get 5.0 degrees C. If you do it in the calculator, you'll just get 5. And you'd think there's only 1 significant digit, but there isn't. There's 2 significant digits here. Okay? Now then, we're going to plug everything into here. So the mass is, let's see, where are we? 20 grams, 20.0 grams, times, and the specific heat is 4.18 joules per degree C per grams. And the change in temperature is 5.0 degrees C. Just to make sure we keep everything lined up nice and neat so we can see how to count. So we put numbers that aren't in a fraction over a fraction, since we're doing a multiplication problem that involves fractions. Now we can see what to cancel. You cancel grams because you got 1 on the top, 1 on the bottom. You cancel degrees C, just like X's and Y's in algebra. Degrees C can cancel. And we're left with joules. And joules measure energy, and we're looking for energy. How many joules of energy is the question? Okay? So we do the math, and this one comes out to be pretty easy. 418 joules. 2 digits. Underline that. Okay? Move our decimal place 2 places. 1, 2. Okay? And you get 4.18 times 10 to the what? Second power joules. Okay? All right. If we have to round off a number in the ones place or a digit in the ones place.
That's the final answer that you got, right?
This is the final answer here.
So I mean, like, when you multiply all that together,
You get this. That's right. But there's only 2 digits, 2 significant digits here.
But you cross that grams and degrees Celsius, so you didn't multiply by 28.5. I mean 5.0.
You didn't cancel out the 5, you only canceled out the degree C.
I was thinking you multiply 20.0.
Yeah. Yeah. Okay. All right, let's look at it. Since everything I have on the paper here is required, I want to give a point for everything on the paper. Okay? There's a point for Q equals M times specific heat times change in temperature. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. That's 12 points total so far. Okay? 1, 2, 3. And because you got to have the units when you add, 4, 5, 6. Okay? It's 12 and 6 is 18 so far. Is that right? Okay. 19, 20, 21 and 22 because you're canceling. 23 for the times sign, 24 for putting it over 1. 25, 26, 27, canceling is 28. 29 and canceling is 30. 31, 32, 33. Over 1 is 34. Equals 35, 36, 37. You've got to underline the insignificant digits. 38. I don't require this right here, so I'm not going to give you a point for that. 38, then 39. 40. 41 for the scientific notation part. 42 points. All right, so solve this problem. You got to get out that graph we did earlier, find the right equation, use the right equation, plug in the right value for the constant that's in there, and solve the problem.
I got like 7 equations on here.
Okay, now can you re-explain the thing you're talking about?
All right, so the way you solve this, you plug in the mass, you plug in the delta H, you find the problem, you find the number of significant digits, there's only 3, and round it off properly, and that's the answer. Now, as far as the homework's concerned, okay, this problem asks you what happens when you're going from negative 5 degrees C, and that's down here where it's freezing, okay, in the frozen range. You're going through, you have to melt it because you're going from negative 5 to 25, so you got to melt it in here, and then you got to raise the temperature to 25 degrees.
Well, what do we put
So-
to change the time?
Just hold on. You got to find the energy from negative 5 up to 0 because it stops going up at 0. Then as a separate calculation, you find the amount of energy required to melt it. And then you find as a separate calculation, a third calculation, how much energy you need to raise the temperature from 0 up to 25.
So you're going to have 3 different answers?
You add them all together to get the final answer. That's right. What you want? You want all that? You got it. You got it. Negative 5 to 0. That's one calculation. From when you're melting, that's the second calculation. And from 0 up to 25 is the third calculation.